Hello everyone, today I would like to talk about what metric spaces are in topology. Metric spaces are pretty useful in topology since they give us distances, pretty much. Now the definition of a metric space is that a metric space is a function on a set that takes two elements of the set and returns the distance between those two elements. Now what does that mean? Here is an example. I have R, the real number line, and these are the elements of the set. R is just a set of all real numbers, and they're all ordered in this line shown here. Now, a metric space is a function on a set, right? And it takes two elements of the set and returns the distance between those two elements. So I can take two elements of the set, like -2 and 1, in the metric. I'll take these two elements and give out the distances between these two elements, between these 2 points, x equals -2 and x equals 1. Here I've drawn the metric for the real numbers. It's the formula that you learn in like grade school or middle school. It's that the distance between 2 points, x2 and x1, is x2 minus x1. So yeah, that's the metric. This symbol might seem new to you. It's just saying that it's a function that takes x2 and x1 and gives you the distance. Here is the function, right, shown here. So yeah, that's all what a metric space is. It's a function on a set, takes two elements of the set, and it returns the distances between those two elements of that set. If that makes sense. Now here are some of the postulates of the metric. Postulate 1, d of xy equals d of yx. This makes sense, right? If we have let's draw the number line again. It's just in that the distance between points x minus 2 and 1 should be the distance between 1 and x minus 2. It's pretty obvious, right? Also, I should have specified this, but dx2 x1 means the distance between x2 and x1. dx1 x2 means the distance is between x1 and x2. And the first postulate is basically saying that it's symmetric. You can switch x2 for x1, your distances should be preserved. This actually plays a pretty cool role in tensor calculus, because of this, the metric tensor is symmetric along the diagonal, but that's too far right now. Well, that's that. I actually talked about that in my geometry series a while ago. But yeah, another postulate is that dx and xm should be gamma and m. Now this symbol I just invented myself. You won't find this in textbooks. I just invented it myself to make the postulates a bit more compact. But yeah, it's true. So dxn xm equals gamma and m, where gamma and m is defined as 0 if n equals m and not 0 if n is not equal to m. Usually in textbooks, they'd make this single postulate be two separate postulates, where d of xy is not 0 if x is not equal to y, as one postulate, say 2, and then 3 would be dxx equals 0. But I just wanted to make it itself one rule to make it more short. So yeah, that's why you won't find this notation in textbooks. The third postulate is that d of xy should be in the interval of 0 and infinity. All this means is that you can't have negative distances. Now there is a caveat to this, because in general relativity, you could have negative distances in space-time. I think that's for space-like paths or something. But normally the distances should be positive. And for dxy should be less than dxz plus dzy. This one might seem a bit foreign, a bit more trivial, but it makes sense when you actually visualize it. Like a lot of things in topology, visualization makes things much more easier to understand. So let's just move this down a tad bit. Okay. So what does this third postulate mean? So the third postulate is saying that d of xy is less than or equal to d of xz plus d zy. Let's just draw x, y, and z. Let's just call this point x. Here is y, and here is z. It's saying that the distance between x and y should be less than or equal to the distance between x and z plus the distance between z and y. It's sometimes called the triangle theorem because it forms a triangle, right? And this makes sense, right? This is the distance between x and y should be less than the distances between x and some other point z, and plus the distance between z and some other point y. Less than or equal to, right? Since like here's a straight line. It's basically saying that the shortest distance is a straight line between 2 points. Because if we veer off from this line, we're going to cover more distance. Now, it's less than or equal to. It can be equal to for the case where z actually lies on that line. Because in that case, then the distance between x and z plus z and y will just equal the distances between x and y. That's where it comes from. And there's a more general form of this theorem, which applies to an infinite number of points that we will be proving in the next couple of videos. So here is another example of a metric on the R2 space. I've seen this one in geometry. The distances between 2 points x1, x2, and y1, y2. I think I actually wrote this one wrong. My bad. This should be x1, x2, and then sorry, oh my gosh, x1, y1, and x2, y2 equals this. So I have some point here, right? This point is like, say, x1, y1, right? And then I have some other point. Let's call this point x2, y2. The distance between these 2 points is going to be this over here. This may seem a bit weird to you, but it's literally just the Pythagorean theorem, right? Because this is a straight line. And here we have like A. Here we have B. And here we have C. So it's saying that A squared plus B squared equals C squared. Yeah. And you can try to convince yourself that A equals x2 minus x1 and B equals y2 minus y1. You can just see it from this picture, but just try to convince yourself with that. So yeah, that's the metric for R2. Now, are there any non-trivial metrics on some geometric space? Well, the answer is yes, there is. In the realm of differential geometry, we often deal with certain manifolds that have some metrics that veer off from the Pythagorean theorem. In fact, the Pythagorean theorem, a squared plus b squared equals c squared, actually only holds for when your space is flat. If your space is curved, this no longer works. And I'll just give you like a sneak peek of it. The length of a vector should be vi vj plus gij. Like we have some vector here. We'd have like v1 here and v2 here. I can be like 1, 2, 3, all the way to the number of dimensions in your space. Same thing with j. So the length of a vector, which is distances between 2 points, like A and B, will be vi vj gij. Where gij is the metric tensor. Now, for the case of a flat space, gij is the Kronecker delta ij, which is just the identity matrix ij. And current curve delta is 1 if I equals j, and 0 if I does not equals to j, by definition, right? So VI VJ GIJ would equal VI VJ. Current delta IJ. So we change the j's to i's, we get VI VI, which is just V1 squared plus V2 squared plus dot 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 Vn squared. If n equals 2, as in the number of your dimension is 2, then we have V1 squared plus V2 squared equals the length of the vector squared. Squared. And that's just the Pythagorean theorem. A squared plus b squared equals c squared, where a is v1, b is v2, c is the length of v. So if you didn't understand that, it's fine. It's not topology technically. It's geometry. I made a video about the metric tensor in one of my early differential geometry series or tensor calculus series. Check that one out if you don't understand how the tensor works, but that's just an example of like how, well, it's an example of how a squared plus b squared equals c squared holds if your space is flat. If your space is curved, and Gij is like some other thing, like Gij may be like, I don't know, 3x plus 3y or something. It could be a field. It could be a constant that's not 1 and 0. Then your metric, the length of your vector. This should actually be the length of the vector squared. Actually, the length of the vector will change. But basically, the length of the vector in general is the square root of vi, vj, gij. An example is like the Schwarzschild metric. I don't know it by heart, but it's like ds squared equals like something. It's not the Pythagorean theorem. I'm going off on a tangent right now, but the basic idea is that metrics don't have to be the Pythagorean theorem. They can deviate from it. The Pythagorean theorem only holds when your space is flat. If it's not, the metric components, the metric tensor components can be like a field, any number of things. So yeah, that's how metric spaces work. In the next video, I'm sure I'll cover the space-time algebra. I've been putting that one on for a long time, but yeah, I hope to cover the space-time algebra in the next video. So yeah, thanks for watching and have a great day. Any questions, you can just write them down in the comments.